Welcome everybody. Hello everyone. So my name is Omar Kuki. I'm professor with ETS, and I've been working on this LTCC technology for a while now. And the goal today is, for my part of the presentation, is to give everyone an overview of how we got here, and then hand it over to the team to tell you more in detail about this. But before we get started, for some of you who are not familiar with ETS. ETS is called the Technologie Supérieure. It is Quebec's largest engineering training school. We produce essentially one out of every four engineering graduates in the province. Today, the school counts more than 11,000 students, more than 30,000 graduates. We have a co-op program that places over 3,500 students in about 1,200 companies yearly, and the school now has grown to over 1,000 employees. One of the school's largest labs is called LACIM. It's the Communications and Microelectronics Lab, and our history with LTCC started around 2008 when I was the director of the lab, and we had the vision in the lab, which was to really equip our lab with a world-class microfabrication and packaging technology, which basically involves these two technologies, LTCC and MEMS. And this was a way for us to complement our strong abilities in design and modeling and all of this stuff, but we were not really didn't have significant technology as far as prototyping and microfabrication. And that was really when we started this process. So what you're seeing today is really the fruition of an effort that started a long time ago and that matured over time. Oops. So really, the way we set this up, and this is relevant to today's webinar, from the beginning, our vision was to have this lab be accessible to a wide community. ATS's slogan is engineering for industry. So it's in our DNA to be open to industry and obviously to other collaborators. So when we did this program, when we started this lab in 2007-8, we had to really build this project with the support, the express support of many companies. So we had industrial support, many universities, also that expressed support for us to go ahead with this project, and even some government labs also were supporting us. So this helped us to convince the administration to invest a tiny amount of money, 1.1 million. And my job was to stretch that money and build the lab that you'll see today. So we were successful with that. And right after, so we actually did everything ourselves to cut costs. So we built the clean rooms and we bought the equipment and we installed the equipment. And so you can see with that little money, we built one class 10,000 clean room for the LTCC, one class 1,000 for the MEMS facility. And for the MEMS, we stretched the budget to put this initial, industry-grade LTCC infrastructure. And this was essentially initially completed around 2009. And then over the next few years, we started building the process, and we were successful in securing additional funding from Industry Canada, another 3.5 million to complete the MEMS infrastructure. And then from that point on, it's really been an effort of building a team. So today our team has grown. When we started in 2013, we had one technician in charge. So today we have a team of 3 people helping us. We worked on maturing the processes that we have, whether it is in the LTCC or in the MEMS, and on building partnerships and servicing the community. And our outreach and our collaboration with CMC is really meant to actually take this to a national and international level, because we believe that today we are at that stage. We have the team, we have the processes, we have the technology, and we have the robustness so that we can service a wider community. So this is the infrastructure as it looks today. So this is our LTCC clean room, and I think the team will tell you more about this machinery and what it houses and what we can do with it. We're not talking much about the MEMS clean room today, but you should know that we have, these are two adjacent rooms. You get out from one, you get into the other, and some of the work we do involves both. So we can do some circuitry in the LTCC room and take it into the MEMS room, and we'll tell you briefly about that as well. Okay. And that's the kind of a brief introduction when we started where we are today. I just want to also let you know that as we move forward with CMC, we're moving in this direction after having really done some some initial collaborations, both industrial, non-academic, and academic with external users. In addition, obviously, to extensive use in our own by our own students and our own researchers. So I didn't put all the internal uses here, but you see here some of these the industrial collaborators that have made use of our facility. And by means of flavor of what can be done, by no means exhaustive, but just indicative of the kind of things we can do and the realizations that have been done over the years. So these are some of the example circuitry that were built. So we've done quite a bit of work on, mainly in the RF area. So we've done quite a bit in lumped LC filters, inductors, capacitors in 3D. And you see some examples of the 3D layouts and the actual fabricated devices. We also pushed the technology. We did, I think, up to close to 40 layers. And we've done circuitry that instead of being horizontal was actually vertical. So you're seeing here a stack of 40 layers, signals going in through the substrate, going out. So this is essentially a nth order Chebyshev filter. And this is the 3 millimeter by 2 millimeter, but by about 5 millimeter depth. And this gave us, for a circuit at about 60 gigahertz measurement and fabrication. So this validated our ability to push this technology to a lot of layers. We've done, for those who might be familiar with this SIW stuff, substrate integrated waveguide. It turns out this technology is very well suited for LTCC, and we are able to do this. So some of the classical conventional structures, but we are also able to do air-filled substrates and doing this for low loss and for very high frequency, V-band, these kinds of things. So these are things that were designed, fabricated, and tested in our lab. Other applications, so we've done quite a bit with amplifiers, power amplifiers, using the LTCC for low loss, matching circuits or combining circuitry, as is the case for very high power. And better thermal management. So this is the kind of stuff we've done. So in addition to the LTCC itself, the mounting, the assembly, and all of that also is something we've done in-house, and we know how to handle high power devices. Further other realizations, other examples. So we can do, so this is stuff I can't divulge so much, but this is industrial usage. So some flip chip interposers, flip chip PCB with a heat sink, some 3D packaging with concealed connection and so on. So this is more elaborate product type fabrications that were carried out on behalf of companies in our lab. And my last example is also we've done some stuff with packaging, custom package with 96 pins wire bondable for VGA application. And we've done even some stuff in microfluidics. And you can see here an X-ray view of, the cavities where we put fluid in, and we can pump it in and out. And we've done this using cavities inside the LTCC. So again, I don't want to take too long because there is a lot of material you want to go through. But this is the brief overview of this technology. And I think at this point, we'll hand it over to Mustafa, who's going to probably give you some more technical detail about the LTCC process.
Hello, everybody. So my name is Mustafa Bellaj, and with my colleague Norman, we will present you the LTCC laboratory process and the capabilities we have in the LTCC fabrication. I'm in charge of the laboratory LTCC since 2 years, so it's not that long, but I'm here since I think 2 years ago. So. What is LTCC? LTCC technology is a multi-layer ceramic technology which provide not only interconnects between the components, but also passive component like capacitor, inductor, and resistors, even in the inner layers of the stack. So the idea of this webinar is to introduce you to the LTCC process. So this presentation will only describe the general rules, and there are possible exceptions, but they have to be discussed without before going too far in the design process. However, it has to be pointed out that the combination of all extremes in the design rules will lead to a very poor yield. So that's we try to not do it. So the LTCC is the abbreviation of low temperature Cofired ceramic. It's a ceramic substrate system which is applied in electronic circuits as a cost-effective and competitive substrate technology with a large number of layers and a mixed layer thickness for maximum 5 mm thickness. So the low line loss as well as the competitive manufacturing cost are an advantage of LTCC for RF and microwave application. It can go up 110 with the tape system we have. So here I'm gonna show you the different step we do in LTCC fabrication. So the process is pretty much straightforward. We first take a green tape with so we cut it, which is shown as blanking on the picture here. When I say green sheet, it means that that is an infrared LTCC sheet that stand over a mylar holding the sheet in the back. So our LTCC production line use a 12 centimeter by 12 centimeter green sheet for the production of the circuits. So the machine we have need a part of the contour of the sheet, so of the 12 by 12 centimeter. For this reason, we have only a 10 centimeter by 10 centimeter usable surface. So before the baking, because the baking has an effect on the sheet. We're gonna see it later what it do. So second, we do the via punch. To do the via punch, we have a punch machine. It's a mechanical punch machine that can only do 150 micrometer via diameter, and we have also a laser machine that can do from 50 micron to 200 micron as maximum, but the 50 micron we can only do it in the 2 miles green sheets. After that, we do the via filling. The step is done. We use gold and silver paste, and it's done using metal stencil. After that, we do the printing, conductor printing, and this is done with the serigraphic, using the serigraphic mask. We print gold, silver conductor. We use silver and gold, and we use the silver for inner layer to get the maximum performance, and use gold for conductors to protect from oxidation. And we can use also a carbon base to create resistors. So then we do the inspection after painting on each layer. On each step, we have to do the inspection, like that. We see all the conductors are good, well printed. So after that, we do we do the stacking and the lamination in a heated isostatic press. After that, like as a last step, is the singularization of the circuits. So this is done with a guillotine cutter if all the parts are well aligned. If not, we can also use our laser machine, and we have more flexibility with our laser machine. So once we cut all our circuits, pardon, the multi-layer ceramic, we fired it, and we fired it in our oven, and the temperature of firing is 850 degrees Celsius for the LTCC glass ceramic. So this relative low temperature enabled to co-firing of gold, silver, and carbon. We can do also some post-treatment, like printing brazing paste to solder or cover ring. We finally do a visual. We can do a visual inspection, and also we test also inspection electrical to test if there is open and shorts. So for the next slide, we see here it's picture of our LTCC lab with the automated lane we have. So it's LTCC production. Our LTCC production is done in 10,000 clean room. So this clean room use the HEPA filtration system to maintain air cleanness level of maximum 10,000 particle larger than 5.5 micrometer per cubic foot. So like that, we have a minimal dust contamination while processing the LTCC fabrication. We also have a complete line production, as we said. It's semi-automated. It's semi-automated line. The majority of equipment are from Keiko brand, and it's Slovenian company. So all the machines are designed to use the same LTCC format for manipulation and indexing. The line is completed by our laser that give us a very flexibility. We can do too much thing with it. And also we have a ATV furnace. It's this one here to fire our LTCC. And we can do pardon. So that means we can do a semi-automated production, and for this we have to place manually the LTCC sheet individually in each machine, but the operation is really automated. That's ensure a quick, uniform, and repeatable processing. While we have a semi-automatic line, we can do a small volume of production that will be consistent from stack to stack, and we can do let's say at least 20 LTCC stack a week, and each stack can contain several pieces, and after singularization. So it means that we can produce several tons of parts each week. After that, I'm going to present you the different tape system we have, also different specificities of each tape system. So we prefer using Ferro because we have a really good relationship with them, and also we have all the combination of paste to do silver, gold, and mixed metal. But we have also a Dipon, and for the Dipon, we have the Dipon 951 that is available in thickness 10, 4.5, and 2 mils. The shrinkage is when we fire our LTCC. So the LTCC sheet's gonna shrink. That's the effect of the firing. We have 12.8% for X and Y, and 15% in the Z. And we have also the electrical properties that the epsilon R are 7.7 0.8, and the lowest tangent we have is 0.006 at 3 gigahertz, and it can go maximum at 20 gigahertz. We have also DPON 9K7, so we have only 10 and 5 mils, and the same we have the X and Y shrinkage is 9.1%, and the Z is 11.8%. For the epsilon R, it's 7.1, and the loss tangent is 0.001 at 10 gigahertz for the maximum use at 100 gigahertz. And now we go to the Faro. We have L8. It's 10 and 5 miles. Available thickness, and we have the shrinkage in X and Y is 13.2, the Z is 30%. For the epsilon R, it's 7.2, and the loss tangent is 0.0022 at 3 gigahertz for maximum use for 40 gigahertz. And for the A6M, it's 10, 5, and 2 miles. And the shrinkage in X and Y is 15.8%, and for the Z is 26%. For the epsilon R, we have 5.7, and for the lowest tangent, we have 0.001 at 10 gigahertz for maximum 110 gigahertz. So that's the specificities we have on our green tape. Faro now has been sold to a company called Vibrant. So we're still using Faro, but we should call it Vibrant for their new name. So it's that's it for my part. I'm gonna let Norman take the rest of the presentation.
Okay, so now so I'm Norman. So I'm working at the LTCC at ATS Labs since 14 years. So I will talk about our standard layer convention for the LTCC design. On this image, you see only 4 layers, but we can do much more layer. I will talk about it later. So this is just an example. So the numbering is starting from the bottom layer to the top layer. So on the bottom you have mass 0 here. That is the back of the layer number 1. So it's generally a ground plane, but it can also be conductors, resistors, or capacitors. It's harder to align from the bottom as it has to be done after all the sheets are stacked. So we don't recommend to have small feature on the bottom prints. In this table, I show the different possibilities that we can do on each layer. So via is the via punching, that hole that we punch between in the LTCC, and we fill it with gold or silver. The metal conductors can be silver or gold, but if you want the maximum electrical performance, you should use silver on all layers. Silver has the highest conductivity and is less costly, but it oxidizes over time. So gold is usually used for exposed metal for the bottom and the top of the stack to avoid oxidation. But if you want to use silver, it will take a few months before you have noticeable oxidation on the circuit, so you have time to test it. So we can print resistors on all the layer, any layer, but only exposed resistor can be trimmed to have a good precision. So if you have buried resistor, you will have up to 30% resistance of the resistance value, as it can be trimmed after baking. So here you have a RA and RB. This is two paste that you can use, two paste resistance that you can use. So you can have a RA for a 10 ohm per square, the B 100 ohm per square, and it can be on the same layer or different layer. So we can also print capacitors using dielectric paste. So the dielectric paste will have higher dielectric constant than the LTCC sheet, because you can also do some interdigit capacitor or plate capacitors that will be placed between the LTCC sheet. Like you can use a 2 mil sheet to have the dielectric, and use the top and bottom metal to do the capacitor plate. So you can use the capacitor paste to have a higher value capacitor. Okay, I will now show you the layer definition that we use on Keysight ADS software. That's the only design kit we have for ADS. So if you if ADS is available if you subscribe to the CMC, so that's the software we recommend that you use. If you use another software to generate your drawing, you should try to adopt the same naming convention. It will help when we import it. We have the following layer definition. So on the right here, this is a layer that we use to do the fabrication. So you will see it on the design kit, but you will not really use it. That would be for us. But that is our the export process. And you can see here the template that we'll have with the design kit. So if you have the design kit, you can put your design inside these box here, because the layer Ferro here and Dupont shows the maximum area that you have. As we speak before, they are shrinkage. So you put your design inside those box. We will enlarge it to the maximum 100 and 100 by 100 millimeter, and when it will bake, it will shrink back to the value that you want. You may count a variation of 1% from what you expect, because depending on the metal, the quantity of metal and via, the shrinkage will vary a little bit. So it can vary like 1%. So you may count 1% variation on the size that you expect. Now and then we have some cutting lines that are used with the guillotine to cut the circuits. You have circuit lines to that will define the boundary of your individual circuits. Mask line are lines that we had to do process control, so those little things here, and it's also used to do the alignment of the mask on the LTCC, and the mask will be aligned with the holes that we do on the LTCC sheet. So those layer here are used for punching the LTCC, and we use it to do the alignment. So on the other side here, you have the design layers. Sorry. So as I told before, metal 0 will be under layer 1. So you can put metal, you can put two types of resistors, capacitor paste, the second electrode for the capacitor. Mask and ablation. So this is used by us. Mask is what we use for each layer to produce our serigraphic mask. So we take the metal, we put it there, and plus we add our mask line inside this layer to do our serigraphic mask. Ablation is used for to do ablation if you want to have very good control of the dimension of your circuit, or if you want smaller than 125, which is the minimum line width. So we use this to structure your design. And you can have ablation brazing, the brazing paste to put cover or something that you want to do after for post treatment. After metal 0, then we start with the real layers. So layer 1, we have the metal, the resistors, capacitors, but in addition we will have the via. So the via, standard via, you will have thermal via if you need to drain heat from power circuit to a heatsink. And you have cavity window. Cavity window can have different use. Like you can use it to drill cavity for to put a high C. It can be flip chip or wire bonded chip, and it can be also closed cavity be able to put liquid or gas as we wish to. So we can discuss it later if you need. And again, we have the mask and ablation mask. So when you want to export your design, you should always use a DXF format in a single file. So all the layers should be in the single file. I didn't say you can have a maximum total of 25 layer. It can be higher than that if needed, but it should never be more than 5 millimeter. Yeah, and the DXF file should be in micrometer unit. You should also make sure that you don't have any polygons for the via, because our punch machine doesn't take polygons. So make sure you have circles. Before you send us your final design, we recommend that you send us early designs for us to validate the export process and to guide you before you go too far in the design if something is wrong. Okay, here's a summary of our design rules. You can have our complete design rules document on request. This is just a summary, very basic summary. So we have 3 sets of rules. You have the standard, acceptable, best effort, or laser trim. You should always try to use the standard rule. It will ensure a good control of the dimensions and a lower fabrication cost. The laser trim should be done on small area as much as possible. It's possible to do large area, but if you want to better control the process, it's better to do it on smaller area. Our standard minimum line width and line spacing is 125 micrometer, as you see here. So the spacing between 2 lines and the line width, so the width of a line should be always 125. The conductor should be at least like conductor conductor spacing to the edge of the part or to the cavity should be 385 micron. But it's possible to have, for instance, pads. You can have pads that you can put closer to a cavity, but we have to check with you if there's no problem, if there's a problem or not. The buried large metal like ground planes and power planes should be meshed with a density between 50 to 75%. 100% is possible, but you may experience delamination of the LTCC layer over time because the LTCC does not stick to metal as well as another layer of LTCC. The via size is fixed to 150 micron before firing because of our punch machine. It's possible to do bigger and smaller, as we discussed earlier. So it's possible to do 50 micron, but only on very thin LTCC layer. So as if you go to a thicker LTCC layer, it has to be bigger because the aspect ratio is important. So the via spacing center to center, it should be 450 micrometer or 3 times the via size. So if you choose a non-standard via size, you should count three times the via size. It's possible to do 2 times, maybe less, but only for small quantity of via in a row or in an array. If you go too close, you may get cracks in the LTCC layers between the via. So, and the via should not be closer than 450 micrometer from the substrate edge or cavities. Again, it's possible to go closer if we give the approval. So ideally, each via should have a catch pad that will be 60 micrometer bigger than the via. So around the via, you want to print a metal to kind of enlarge the area. So it will be to ensure a good electrical connection to the upper via. So on the top of the sheet, the next via may be misaligned when we stack it. It's not always perfect, because the tape may shrink a little bit while we manipulate it. So you can count a few tenths of microns it should be less than few tenths of micron when we stack it. But so if you put a catch pad, you will make sure that your via will do a good connection. We work on a 100 by 100 millimeter surface on the LTCC sheet. So after the shrinkage, you will have 79 to 89 millimeters square of usable surface, depending on the tape system. And the minimal part size is 2 by 3 millimeter. Again, it depends on the thickness. So we cannot have 2 by 3 millimeter for a 5 millimeter thick. There's an aspect ratio to take in account. So contact us to get the design rules if you need to do resistors, as shown here, capacitors. If you want to do open or closed cavities, just contact us and we will share it with you. We presently have a design rule checker for metal and via for ADS software. It is included into our design kit library. This is the end of my presentation. I will now give the presentation control to Ines. Thank you.
So, hello everyone. I'm Ines. I'm a PhD candidate in Professor Cookie's team. I'm also working as the MEMS clean room manager. So we were talking about the fabrication. Now, to validate the fabrication aspect, as we are working with a 3D structure, we may need microscopy tools and 3D tools, 3D inspection tools. So we are equipped with several microscopy and tomography tools, such as the confocal microscope. We have also a scanning electron microscope. We have the Cayenne optical microscope, and we have the X-ray machine. So with those equipments, we are able to produce high-resolution images, and we are also able to perform 2D and 3D contactless measurement. With the X-ray, we are able also to inspect the internal structure, as we can see here in this photo, the internal structure of our substrate, especially when we are using LTCC, and we can have internal components or fluidic cavities. Also, we are equipped with the KLA profiler. So with the KLA profiler, we can perform 2D and 3D measurement, such as the roughness and the waviness, that are the parameters that are very important for LTCC. We can also perform thin film stress measurement. Also, we can measure the sheet resistance and the resistivity of the surface using the 4-point probing method. We can measure also the impedance, the dielectric impedance of the substrate or the circuits using a spectrometer. And last but not least, we can use our thermal camera to inspect the thermal behavior of the circuits, especially if we are using thermal components. Now, before moving to the measurement, sometimes we may need to do packaging if we are not able to insert connectors or using point measurements. So in our lab, we are able to perform either wire bonding or flip chip. And both processes are well established for LTCC technology. For the wire bonding, it is applied also for commercial IC. It can be applied also for commercial MEMS, for photonic chips, and can be also used for customized circuits such as PCB or LTCC technology. For the flip chip, it can also be used for several technologies. It should just respect some criteria related to the component size, the working area, or and the substrate size. So moving now to the measurement, here is a list of some of the equipment that we have. I'm not going to pass through all the details, but it is worth mentioning that with our 4-port probing station and our 4-port network analyzer, we are able to perform up to 67 gigahertz measurement, such as S-parameters measurements, noise figure. We can also measure nonlinearity parameters, such as the gain compression, intermodulation, and harmonic distortion. We can also perform signal analysis in high frequencies. And with all this equipment, we can ensure the reliability and the precision needed for LTCC characterization. So with the effort of our research team, also we are now able to perform lithography on LTCC. So basically our MEMS clean room is equipped with the necessary tool to perform the conventional MEMS process. So with the LTCC substrate now we can integrate components inside the layers, and we can perform microfabrication on the top of these layers. However, the ceramic roughness is not really appropriate for microfabrication. That's why polishing was needed. So here is the photo before polishing, and we can see here after polishing, we are using a chemical mechanical polisher. Here's the process for to do so. So here is the LTCC process that my colleague has already explained. After that, we need to polish the resulted substrate to reach around 25 nanometers roughness. So if you have internal component, we will need to do an alignment. So a picture of the polished substrate will be taken and then converted to the DXF. And after that, this DXF will be the DXF of the lithography mask will be aligned using the DXF that we have after the polishing, and with this mask DXF, we will use it for the lithography. So my part is already finished. I will pass the control to Professor Cookie.
All right, so thank you, team, for the presentation. I hope the information was clear. At any rate, there is always this recording we can probably go back to. So before I talk about the resources, I just want to get back to this CMC collaboration. So today we wanted to give an initial introduction. We cannot obviously go into so much detail that would be needed for somebody to use the process. And for that reason, I think there is a plan with CMC for following subsequent actions. Namely, we're planning a training course that can be over a couple of days to make sure that those interested in using the process have the necessary skills and the necessary training to be efficient in using this. So the goal is obviously to give you the support, all the support needed to go through this, including the training, and then during this design and fabrication phases as well. With that, what you see here is a list of the resources. So this information, if you go to ltcc.etsmtl.ca, you'll be able to get access to documents. So, some of the stuff that we talked about, description of the process, the design rules also are available upon request, but the detailed specs of the taping system that we use. And you have in this screen, you have the information about our contact information for any additional questions. And obviously, there will be a channel through CMC as well